Okay, so in this video, I wanted to go through the iodine thiosulfate titrations, but just before I start into that, I just want to quickly revise the idea of limiting reagent again, okay, or limiting reactant. So, like, if we just use an equation here, like iron and sulfur making iron sulfide, like you would have done in first year. If I said to you, we're using 4 moles of iron, 6 moles of sulfur, what would be the maximum number of moles of iron sulfide that we would be able to make? So you need to think about that for a second. Okay, so 4 moles of iron, 6 moles of sulfur. What was the maximum number of moles of iron sulfide that we'd be able to make? Well, 4 moles of iron sulfide. Because look, you only have 4 moles of iron. The ratio is 1:1. So when 4 moles of iron reacts, 1:1, you're going to have 4 moles of iron sulfide made, okay? Once all of the iron is gone, your reaction is over. So we say that the iron is limiting the reaction, or is the limiting reactant, limiting reagent, something like that, okay? The sulfur is in excess because once 4 moles of iron reacts with 4 moles of sulfur to make 4 moles of iron sulfide, because your ratio is 1:1:1, you will have 2 moles of sulfur left over. So the sulfur is in excess, the iron is the limiting reactant. Now, just before I go to the titrations, what does it mean if the iron is the limiting reactant? Remember, all of the iron reacts and the maximum amount of iron sulfide is made because all of the iron reacts. Okay? Now, just a bit of theory quickly on the iodine thiosulfate titrations before I do an example of one. So, first of all, this is a little bit different. It's definitely the hardest type of titration, I think, because you don't have a standard solution starting off. Remember that? So, like, the problem here is that neither iodine nor thiosulfate are primary standards. Now, you need to know the reason why. Iodine's not a primary standard because it doesn't dissolve in water. It's not soluble because, look, it's a non-polar substance, isn't it? I wouldn't expect a non-polar substance to dissolve in a polar solvent like water. So it's not soluble. And also the issue with iodine is that it sublimes. It goes straight from a solid to a gas, so it's not stable. Thiosulfate's not a primary standard either because it's not pure. So we have a problem. Always in our titrations, we have a solution that is a primary standard, or a substance, that is a primary standard that we have made into a standard solution. We don't have a standard solution of either of these two reagents that we want to titrate. So the question is, how do we get a standard solution of iodine? Well, we use this equation here. So look, we're back to the permanganate again that we were using in the previous set of titrations. You have standardized permanganate. So what does that mean? You know its concentration. So if you use this permanganate that you know the concentration of to make iodine in the conical flask, then you can calculate the concentration of the iodine. Now, the only thing is, the permanganate has to be the limiting reagent or limiting reactant. So all of the permanganate will react and you will make the maximum amount of iodine according to the ratio there of 2:5. Okay? Now, they might ask you the question in the exam paper, why is the Ki in excess? Now, the reason the Ki is in excess, so the Ki is added to the conical flask to supply I- ions. The reason that the Ki is in excess is so that the KMnO4 is the limiting reagent firstly, because this is what we know the concentration of. So we want this to determine how much iodine is to be made. So 2 reasons for Ki being in excess. One is that the permanganate is the limiting reagent. And the other reason is, look down here, we said iodine wasn't fully soluble. So the iodine doesn't really dissolve in solution in the flask. So we get the extra I- ions that are left over because the Ki is in excess to react with the iodine that you formed, and you make I3-, which behaves the very same as iodine, but it's soluble. So just to recap now, how do we get a standard solution of iodine? We're going to put KMnO4, Ki and sulfuric acid, look, KMnO4, Ki and sulfuric acid into the conical flask, and you see the red-brown colour of iodine being formed in the conical flask, okay? So we can now calculate, because the KMnO4 is the limiting reagent, we can use the ratio of 2:5 and we can calculate the concentration of iodine that's made in the conical flask, okay? Now, Just the last bit of theory I want to run through with you. The indicator that we're using for these titrations is starch. We don't add starch at the beginning, which is very unusual. We normally would add starch or the indicator at the beginning of a titration. Remember now at the start, the contents of the conical flask is red-brown because you've got iodine made in there, okay? So we wait a while. We're going to add sodium thiosulfate to the conical flask from the burette until we see it, contents of the flask turning pale yellow. Once the contents of the flask have turned pale yellow, a lot of your iodine has actually reacted with the sodium thiosulfate, okay? Then you add the starch, plus starch and the remaining iodine turns blue-black, and then you continue to titrate until the blue-black turns colourless. Then all of the iodine has reacted. All the iodine is gone at that point when you see colourless. Now, the reason for adding the starch at the pale yellow stage is if you added starch in at the beginning, then what would happen is the starch would, what's the word? Adsorb, isn't it? Adsorb onto the iodine. And if the starch adsorbs to the iodine, then the thiosulfate, the sodium thiosulfate, can't react with the iodine and you're going to get an inaccurate result, okay? So you want the sodium thiosulfate, the volume of sodium thiosulfate going in, reacts with all of the iodine. You don't want starch bound to iodine because then if the starch has bound to iodine, the starch won't be able to react with the sodium thiosulfate. So you wait actually until all of the most of the iodine is gone. It's gone pale yellow. Then you add the starch. That will turn the remaining iodine blue-black, and then blue-black to colourless is your end point. It's more accurate titration that way. Okay, thank you.